Okay, good morning everyone. I'm here to review Baryogenesis and Leptogenesis on suggestion from Sri Rup. So I want to thank the organizers for inviting me to this very nice meeting at a very nice venue. And I will immediately issue a few caveats that this topic is far too vast and there is a lot of activity and it actually links to a lot of phenomenology, non-accelerator, collider, as well as astroparticle, as well as cosmology, I should say in general. So I will give you just a very little glimpse based on my limited knowledge of and my own predilections in the field. So, so I plan to cover something like this. First, the very core thing of, so the subject has quite a bit of history by now, and the conceptual bases have been shifting a lot, and it is good to review the ideas that are already sort of discarded, but because they were the original ideas, and they illustrate how the mechanisms may work, and they may even come back, we never know. So I will tell you about gut scale baryogenesis. Then there was some excitement in the 90s about TeV scale or electroweak baryogenesis. And then leptogenesis has sort of remained evergreen. And the scale of leptogenesis has been sliding all the way from gut down to again close to TeV scale. So leptons, because there are so many uncertainties about them, it's possible to tune them to what you like, and a lot of ideas have emerged along these lines. I cannot cover this topic of baryogenesis without going into a bit of physics of the Sphaleron. So it's going to be a little pedagogical, but it is really a very core concept to everything that is going on. Then I will focus more on leptogenesis because it seems to be at present the most promising among the scenarios that invoke basic particle physics, and especially this so-called resonance enhancement and soft leptogenesis, things like this. I have added here a Fleck-Dine mechanism which comes from SUSY flat directions, but I'm not going to be able to touch that at all. But now I already said it, so you know it exists. And then I will try to present our own ideology a little bit from d-parity breaking and domain walls rather than through particle physics decays. So this is a sort of more a collective phenomenon rather than individual particle physics decays. And then this again I'm only mentioning, you will see what I need to say. We have to put it all together after we think of some recipe for generating the baryogenesis. Eventually it becomes necessary for us to link it to everything. And there are several efforts in this direction as well. So the whole idea that baryogenesis exists and needs to be considered originates with the originators of Big Bang, and their photographs are almost never shown, and this history is rarely covered, so I thought that I should cover that. I think a lot of you know that there was a so-called alpha, beta and gamma paper in 1948 which estimated helium to hydrogen ratio by considering nuclear interactions, which has now become a full-fledged subject under Big Bang nucleosynthesis. So this was the first paper, and the author list is in quote marks because actually it was worked out by Alpher, who is in the middle, and Gamov, who was an immigrant from Soviet Union. But Gamov had a sense of humor, and at least in my time, his books were very popular, his popular books. So Gamov said, this Alpher and Gamov, this makes it more complete, you know, it's like Greek alphabet. So although they were in Columbia and Beta was nearby, they added, so Gamov, the senior author, just added Beta's name without even asking Beta and sent off the paper. So later Alpher was a bit sore about it, but that's the way it is. So it's called alpha beta gamma paper, and it did create some excitement. But actually, if you now read Wikipedia, Alpher was the guy who really was working in various applied labs and knew about nuclear interactions. So he understood all of this much better. And then he inspired or collaborated with this Hermann, who was a little older than him. He was also mostly doing technical work in the laboratories in the Northeast area during the World War. So both of them then collaborated just a year later to produce the paper which now we know as cosmic microwave background, and they estimated 5 Kelvin, which is pretty good for 1949. So these are the pictures, Gamow, Alpher and Hermann. Hermann later became a civil engineer analyzing traffic flow using his modeling techniques, and then was in Texas, Austin. What is important to note is that these two events that were analyzed especially by Hermann in both of them, one concerns the MeV scale and nuclear physics, the other actually concerns atomic scale, and therefore EV scale. So there is a million factor between them, and it's amazing that both of these events are the key insights we have into early cosmology today. So the other interesting thing one of the exciting things to happen, that was late 40s, and by 1963, this discovery of CP violation directly was observed, Cronin and Fitch and Cronin, and there is some schematic here to show that 3-pion decay would take much longer, but occasionally the 2-pion decay, which is prompt because of the large phase space, can also occur much later, and this was discovered by them in 1963, and they got Nobel Prize in 1980, whereas the cosmic microwave background was discovered in 1965, and they got their Nobel just 2 years earlier in 1978. So all these developments were happening about the same time and were recognized. So Penzias and Wilson, as you know, discovered microwave background more or less by accident as electrical engineers. But these two things together, the discovery of CP violation and the establishment of the Big Bang as a picture of the universe. You know, until then it was all a matter of conjecture and there are many ideas about cosmology. But this discovery of the hot gas remnant convinced everyone that there was a Big Bang. And this is what led to people beginning to think in terms of predicting or post-dicting the baryon asymmetry. And there are several people who came up with this idea, but the best known model is of Sakharov in 1967. So these are just some of the numerical details. But so I would say this candle of baryogenesis that we have in the sky is half lit because it is non-zero, but then it is half dark because it is much, much less than 1. And so if baryon number was fully violated, then it should be in large abundance, random of course. But if it was not, then it should actually be much smaller. So it is a very interesting candle into fundamental physics. So this is a short pedagogical review of what exactly the originators of baryogenesis thought, including Sakharov and Yoshimura and Weinberg after the guts were proposed, is that there is some way of some heavy particle decay by two different channels, both of the two channels violating baryon number by different amounts. This was important if you didn't know the quantum numbers of X. So it was necessary to have two different modes of decay. There should be charge conjugation violation so that X bar decays are not same matrix element as X. But you also needed CP violation, that is the rate of X going into QQ versus X bar going to Q bar, Q bar. The R1 and R1 bar should be different. But much more importantly, even if all these are satisfied, even if the rates are unequal and charge conjugation is violated, in thermal equilibrium you would have chemical equilibrium and there would be no asymmetry at all. So there have to be some out of equilibrium conditions so that reverse reactions don't equilibrate the products. So here is the little algebra that if there is rate R1 and delta B1 type 1 and B2 times 1 minus R1, assuming there are only two rates, then you find that the net baryon asymmetry produced is proportional to the difference of the two modes of decay, the baryon number in the two modes of decay times the difference of the rates. So this is a simple pedagogical example to understand what are the key ingredients. And finally, to have the asymmetry, you needed the out of equilibrium conditions, you needed the rates of decay of the X boson would have to become smaller than the Hubble constant, Hubble variable at that time in cosmology. However, and of course you need CP violation, which comes from interference of diagrams, as we will see later. But by 1990s, protons were refusing to decay, and so gut baryogenesis was not quite taking off the ground. Now I will switch to another very basic mechanism which concerns the TeV scale violation of baryon number. And although this was like a very obvious thing, it took quite some time for it to be realized. There is a topological solution in standard model called the Sphaleron. And although topological solutions were avidly explored in the mid-70s, nobody seems to have noticed the Sphaleron sitting in front of them for quite long. But Klinkhammer and Manton in 1983 worried about it a lot and very carefully explained that there is actually an anomaly in the standard model and that it is mediated by presence of a topological solution. You can estimate the rate by presence of this solution. So that at zero temperature, it would go like the Euclidean action of the exponent of the Euclidean action of the Sphaleron. And at finite temperature, it would be determined by ratio of the energy to the Boltzmann factor. Both of these numbers approximately, at least at low temperature, are proportional to W mass divided by alpha, sorry, not square, alpha meaning the square of the coupling of weak interaction. So it comes to several TeV. So this object is now ripe to be sort of occurring in our colliders, and there should be some excitement about them. And at high temperatures, this Boltzmann suppression also goes away, and this B plus L would be freely violated. If there is time, I will cover it a little bit through a picture. Okay. So based on this Sphaleron idea, Kuzmin-Rubakov and Shaposhnikov came to argue that there are at least two obvious conclusions. If there is any B plus L generated high scale, it will be erased by Sphalerons by the time you arrive at the electroweak scale. But then there is in fact a way to violate baryon plus lepton number as we cool towards electroweak scale. And now if you are going to use this to generate B plus L asymmetry, then you cannot rely on computation with the Hubble rate of the universe, but you need first order phase transition. You need some the phase transition to produce out of equilibrium conditions. And the story, however, was in the 90s it became clear that the first order phase transition in standard model would require the Higgs to have mass less than 90 GeV. And at that time Higgs was not discovered, so people had the carrot hanging before them for quite a while. I don't know how this slide changer works. Good. So, whichever way you do it, if you wanted to do the baryogenesis at the electroweak scale, you needed this ingredient. Now, it was not competition with the Hubble constant of the universe. So, you needed some bubble walls to be expanding, and because there is a phase transition, phi equal to 0 is the false vacuum, and the universe is cooling towards phi not equal to 0. So there is a wall separating these kind of phases, and the walls have a one-way progress, so they induce a time asymmetry. And there were two generic models, one that relied on walls being thick, one that relied on walls being thin, and there are details of those calculations, but this is whatever you wanted to do, even after extending the standard model suitably, eventually you had to rely on bubble walls if you wanted a low scale baryogenesis, because at low scales the Hubble constant is far too small and you can't compete with it. So this is those are the statements, but the problem was the CKM phase required was also too small in standard model. You could make 2 Higgs doublet model at least. So there was a need to go beyond standard model because the phase CP violation was too small. You could invoke 2 Higgs doublet and it works. MSSM is realistic, but MSSM itself is now becoming doubtful. The one observational possibility associated, if bubble walls was the source and they occurred at low energies, is that we could be seeing gravitational waves from these bubble walls. This is really too futuristic even for current or even the next generation gravitational wave detectors, but it is certainly being considered very seriously. So now I go to the third thing that I said was evergreen. So how much time I have? Yes, another 15 minutes. So the evergreen one is leptogenesis, and it works similar to baryogenesis. And the CP violation comes from interference of tree diagrams with loop diagrams. I think I can go a little fast over here. But what is appealing is that the heavy neutrinos, which are Majorana particles and violet lepton number, are very much on the table. But there is an interesting way that this gets constrained. This is one detailed analysis by these 3 authors, although they were not the originators, but they did a very detailed analysis. And you can have the required baryon asymmetry as a function of small neutrino mass. See, because now you are relying on the heavy neutrinos, Majorana neutrinos, their mass is related by seesaw to the small neutrino masses. So you can actually constrain your model by checking, depending on the value of the heaviest of the small neutrinos, what is the baryon asymmetry produced. And they found that there is a narrow band of m nu that allows this. Fortunately, it falls bang within the range that is now being observed in the small neutrino mass squared differences, and that is the correct range for this. But they found that there is a front factor. The required Mn has to be large enough so that m nu goes in the correct range and you get the correct abundance. You need at least Mn greater than, the heavy neutrinos heavier than 10 to the 9 GeV. So now if you are going to invoke very high scale physics, then you needed to stabilize that, stabilize electroweak scale with respect to that. So you would need at least, I mean, the most plausible explanation would be supersymmetry. But then there would be problem with gravitino abundance if you had to reheat to such high temperatures. So this was not a very attractive possibility. What is happening? Yeah. That is their estimate of the initial abundance. At the temperature you start, it's a fractional abundance with respect to the rest. I think it is a representative number. No. Why is the initial abundance of the heavy neutrinos in the thermal baths when the decay starts? It is number of neutrinos versus rest of the sloop. It's the ratio. It's the Yn of Boltzmann equations, not. Yeah. The other interesting thing was that Davidson and Ibarra estimated this very nicely. They pointed out that the mass m, which determines the decay rates of heavy neutrinos, enters also the CP violating diagrams. So CP violation is determined by the same m's, and the m is determined by the small neutrino masses through seesaw. So knowing the small neutrino mass, you can estimate how much CP you can get depending on the value of the mass here. And they found a number that again comes out too small if M3 is in the correct range, and if M1 you try to put at the scale that Buchmuller and people have found. So this also causes a problem. So the point is that the plain vanilla electroweak baryogenesis doesn't work. The plain vanilla leptogenesis also doesn't work, and gut scale baryogenesis, of course, not working. I think I will skip this. I had kept these slides to explain what the Sphaleron was, but I think I can skip them. I can just say that the postscript is the Sphaleron has now been analyzed again at the very high scale of 125 GeV Higgs after 2012, and you can only do numerical simulations to calculate the rate of decay. It is log gamma over T and versus gamma. But the possibility that B plus L violation may be seen at colliders exists, but it looks unlikely that the Sphaleron is useful for producing baryon asymmetry, but it will definitely erase B plus L produced above the electroweak scale, and you have to take account of the Sphaleron washout rate when you do any baryogenesis calculations. Okay. There are ancillary observables that will restrict any kind of new physics you introduce to explain baryogenesis. One of them is electron dipole moment. So I will just mention that. I don't know how to operate this, I think, here. Good. So then, if everything is ruled out, what are the choices that the Ralte have, as Einstein would have asked? And my caveat is that the only, since B plus L is being violated and not a good quantum number, we can focus on B minus L. And, so B minus L could be global and could be freely violated, then we really have no control. So the red is the preferred path, is what I'm going to argue. What would be nice is this B minus L, which is the only conserved quantum number of standard model which is not gauged. It should be a gauge symmetry, then it would be reasonably controlled and fit elegantly with other symmetries. It should be spontaneously broken, and then B minus L could be spontaneously created after it is broken in the vacuum. And that B minus L would be processed by, well, so heavy neutrinos, when they come into equilibrium, that Y factor of Buchmuller and company, it would begin to erase the rest, B minus L. And then Sphalerons would deplete from them a B plus L part, so that you would left with the residual correct value of B minus L. So that looks like the correct path to go. The only question is whether you go through detailed particle physics, through interactions of particles, or go through macroscopic objects like domain walls. I think this is basically the two alternatives left. And neutrinos are certainly the way to go because they have direct connection with B minus L symmetry. And we already have considerable data on the light neutrinos. So here is how leptogenesis seems to have been salvaged of late. It's almost 20 years now, but it took people quite some time to realize what were the merits of this model. And now there are many, many variants and many ways to complete and relate this model to others. Basically, Pylapsis and others realized that in CP violation, the diagrams to be considered were basically the tree diagrams interference with one of the two, either with the, so the thing that was considered at first was with this vertex diagram, obviously. People would say decay, I showed you this diagram first, and decay with a loop. This kind of interference is what is called epsilon prime in the KK bar language. But people realize that because there could be several neutrinos, heavy neutrinos, which are not too far apart, their loop, the mass correction on the external line would enter also. And this is sort of the mixing or the epsilon-like correction to CP violation, origin of CP violation. So both of these had to be considered, and you had to decide which was the more important. So CP violation from interference with tree level and absorptive part of the loop diagrams, either epsilon type or epsilon prime type. But epsilon type can actually become much larger and can be order 1 if the mass difference of heavy neutrinos is of the order of their decay widths. So if you fine tune the model somehow and say that the delta m is comparable to the decay width, the mass itself, decay widths themselves after this interference, then you have the possibility of enhancing epsilon greatly. But this requirement subsequently has been realized by the same group that it actually enters into QFT interpretations of this perturbative interpretation of CP violation origin. But then, so there are resummations and various techniques being used to see, to validate this particular mechanism. But most people take it as a plausible and a working mechanism. And this is Pylapsis's sample results of this resonant enhancement, and shows that things work well and produces the required 10 to the minus 7 according to him. To begin with, you have to have a large B minus L produced so that you dilute it with sphalerons later and obtain correct baryon asymmetry in the end. So there is a working model for this. As you can see there, the delta M is 10 to the minus 9. He has to choose difference of masses to parts per billionth. But then it works with the epsilon that the light neutrinos would give. So this is some of the things we have been thinking about, that why don't we think in terms of a specific model, and left-right symmetric model is a good one to work with. And most people have been focused on heavy neutrinos that are very heavy, because in the seesaw formula, they put the Dirac mass to be at the Higgs wave scale and put the light neutrino mass. But we have no idea what the Dirac mass should be for the neutrinos, because we know in the charged lepton sector, it ranges all over from MeV to GeV. So if you put MeV scale instead of 100 GeV, then of course you bring down the heavy neutrino mass scale to whatever you like, fairly close to electroweak scale. And in fact, Pylapsis's results also say that because the CP is very high, you can actually bring down this and then evade the gravitino bound. So it is easy to get, of course we have to search for mechanisms that would produce this kind of Dirac masses, but there is nothing saying that the heavy neutrinos have to be very heavy. But now that we are at very low scale, we need mechanisms that would produce adequate baryon asymmetry. One of this is the resonance method. The other is just to have large CP violation in domain walls. And so this was just some tutorial on left-right model. You know, you get very neatly, you get the extra charge that you introduce is automatically B minus L, because it's the same for all leptons and same for all baryons. So in praise of B minus L, it's the only conserved charge of Sm, which now gets gauged. So this is a specific model. A lot of people discuss left-right model in this conference, but this is a specific supersymmetric one due to the ICTP and University of Punjab group, I'll broadly say. So that in this, it turns out that the B minus L breaking scale squared is a product of electroweak scale and right-handed scale. So in this, SU2R breaks first to U1R. So these are the authors. SU2R first breaks to U1R. That sets the scale of MR. And then the B minus L breaks later. So B minus L is geometric mean of these two scales. So you can have reasonably low scale leptogenesis in this model. And we have simulated domain walls in this left-right symmetric model and shown that there can be adequate CP violation. It's the ratio of this real part to imaginary part of K, whichever those lines are. At the peak, you can see that there is a large difference. So this ratio is what determines CP violation for neutrinos that would stream through this wall. So this side is left-like, this side is entirely right-like, and neutrinos that are passing through this according to a mechanism I mentioned in the very beginning due to Cohen, Kaplan and Nelson, thin walls, it would give rise to CP violation. So this is a source of non-thermal leptogenesis and non-perturbative mechanism. So if N mass is not as high as required for thermal leptogenesis, do we have the scope for producing baryon asymmetry? Answer is yes. So these are the various things. Actually, this should have been before this slide. Okay. So the open question is about relating. So if we do this, we do get large CP violation in the domain walls, but then we face a serious problem from science point of view. It would be like this cow eating grass and disappearing, and we would have nothing left. So the CP violation that occurs inside the domain wall, we should be able to relate it to asymptotic values of CP violation and then see them in some experiments. So that is the one open question, and at present I don't know how to address that. And then the question was, if you produce the, asymmetry at such a low scale, would it survive? Somehow this picture has become very small, but we find that there are large regions in parameter space where the asymmetry would survive and can be processed entirely by sphalerons to produce the required asymmetry. Okay, and here is one I meant to include. I actually did go through a lot of contributions from India in this. There are quite a lot. But I just could pick one for immediate purpose, which relates it to specific observables that may be observed in colliders. So this particular paper talks about the washout factor due to sphalerons with this particular value of right-handed W's, so that they could be actually seen in colliders. And our analysis is compatible with this kind of WRs. Okay, so that was, sorry. Yes. So the question then is, if we have this kind of model at a low scale, is there a scope for unification? And we analyzed this, and I included this slide especially because somebody is in the audience. So you can actually have unification of such models as well. So now, what are the things I have failed to cover or are impossible to cover in a short talk? One is the Affleck-Dine mechanism, as I said. This, lot of the supersymmetry people are very excited about it. It is a completely non-perturbative mechanism and a semi-classical one, in the sense that there are a lot of flat directions in supersymmetry and they become unstable at some later stage, and then the vacuum begins to roll down one of the flat directions. If one of the flat directions had a non-zero baryon number, then you would have large baryon numbers stored in the vacuum to begin with, and when you come down, somewhat like inflation where you release a lot of energy, here you would release a lot of baryon number. I find it very difficult to make any quantitative estimates with this model, but it's very popular. There is soft leptogenesis, which comes from soft terms in models that incorporate the right-handed neutrinos, but they do rely on the resonant mechanism of Pilafsis. And the other thing then to think about, so we have plausible models, there are working models, but all of them require some serious extension of the known physics. We should then, because this is all free for all, we should try to cross-check it with all the other phenomena happening in the early universe and colliders. One of them is, so these are all put it all together models. One is called new MSM by Shaposhnikov and Leiner, Shaposhnikov, Asaka and various people. And they basically invoke just three sterile neutrinos. Those neutrinos don't even sit in any gauge group or anything. They are steriles, and then they have ways of arguing that it fits, it can produce everything. But they do not push it as like a realistic model, but they basically argue that just adding three neutrinos is sufficient to produce all the cosmological signatures. There is a model that Ringwald and group have been proposing, which they call SMASH, and I wrote down here because I would forget myself what it means. A standard model plus axions as dark matter, seesaw of course to have the neutrinos, and then Higgs portal inflation. So the seesaw would produce the heavy right-handed neutrinos and give baryon asymmetry. And finally, the Higgs would produce inflation. So they call it the smash model, and they try to fit all the parameters together to show it is working. Of course, at this conference yesterday, we heard Professor Parida's talk, where also he puts together all of the ingredients of early universe. The other major topic is connection of any physics that does lepton number violation can potentially be connected to colliders. So that is beyond me to cover. And finally, I would mention that there is the exciting possibility, although it would not prove anything about baryon asymmetry, it would, if we observe any B plus L violation signature in the colliders, we would be sure of the Sphaleron mechanism as a washout mechanism in the early universe. Wow, sorry. So I tried to put in a few figures from just very recent papers. Have I mentioned them in the next page? Somehow the graphics have come out very bad. Yeah, so this is paper of Sarma, Caprini and Dürer around 2009, first proposing domain wall collision, bubble collisions producing baryon asymmetry. And then they have some results about the spectrum of gravitational waves that would be produced. I can bring up the better pictures, but anyway, right, the PDF somehow didn't convert the postscript very well. And there is I saw a very recent paper from a Japanese group, which has much more detail of how the bubbles collide, and then they also produce a spectrum. So I think of the two alternatives, one whether you are going to go through resonant leptogenesis path and enhance CP, or you are going to have bubble walls and produce baryon asymmetry, may get decided by whether we observe gravitational waves from this colliding bubble walls. Of course, even if you observe colliding bubble walls, it will not prove that they produce the leptons, but lepton asymmetry, but anyway, it would be certainly a confirmation. So I will now just go over the conclusions that extensions beyond standard model accommodating massive neutrinos are required beyond standard model, that's minimum. And then you would require CP violation, which may come either from the interference of diagrams or from domain walls. And you have to ask how the out of equilibrium conditions come. Thermal leptogenesis is certainly viable and appealing, but needs to rely on resonance and effects of this kind. Many other variants of this resonant version are not necessarily thermal. So although I call this thermal, there are other models which have non-thermal versions, which don't rely on thermal equilibrium having been achieved and competition with other phenomena and so on, but they nevertheless play out using, relying on CP violation for resonance. But they all rely on particle interactions in detail, and they enter into QFT subtleties. There are many other sources of constraints, collider as well as non-accelerator like EDM and so on, that would constrain anything that you try to do to extend the standard model. And we do have these put it all together models. We have presented a particular way that non-thermal leptogenesis could be carried out in the course of domain walls in a specific left-right symmetric model. In those things, domain wall disappearance would be certainly a requirement, because you don't want domain walls to hang around till the Big Bang nucleosynthesis. That would constrain the model, the fact that it has to disappear. It would actually give you back something about the model itself. And if that was the case, then there would be gravitational waves as a signature. So that is, I think, my summary. And I thank you all, of course, but also I want to advertise this software which I have been using for a long time. So whatever deficiencies of tiny figures you saw are due to techniques, but also the advantages. Yes. Yes. So it puts together the dark energy, dark matter and collider. Thanks. I think there is a large number of, yes. Yes, it would work quite well with non-supersymmetric theory, except that, yeah, so you would have, so in that picture, the left-right scale is a PeV scale. It's just another 3 orders of magnitude nearby. You can live with a little hierarchy there. Then you would have all the physics coming from that era, but then you would have to protect that scale from Planck scale. But as far as the basic physics goes, it would all work because we have only done proof of concept, and that would, it's not very sensitive to the details, whether the supersymmetric version is there.
It will form actually cosmic string.
Which is both our dear subject.
Which will produce baryon asymmetry.
Yes, yes. That's also, oh, that's right, that's right.
Yes.
One of the oldest non-perturbative proposals is due to Pijoosh and W.B. Kibble. And also I should say in my thesis in 80s, we had another one where, so if you have topological defects, then they have fermion zero modes on them, and they produce very unusual non-perturbative effects. So you can actually have baryon number generation from cosmic things as well. And actually we collaborated on some of it with Narendra too. Okay.
Okay, if there are no further questions, let's thank Urjit.